All right. Today is the 24th of February, 2026, and New River is on a 4-hour delay, which means that no classes can meet on campus. So rather than lose a whole day, I'm going to Zoom. I am Zooming the class for today from home. Excuse me. Homework for Chapter 8 and Exam 3 on Chapter 8, they're due by midnight tonight. And I'm going to introduce now a material for Exam 4, which will cover Chapter 6 and Chapter 7. We'll do Chapter 7 next Thursday. Introduce that material. So let's get started. Well, first of all, actually what I want to do, let me stop this share. And I want to share materials that I would have handed out in class, so that you'll know what you're looking for in Brightspace. First of all, of course, the PowerPoints are self-explanatory, but I also would have handed out this document. I think it looks like this. But it includes helpful hints on how to balance chemical equations. And we're going to go through these in the discussion that follows. But this document is available in Brightspace for you to hold. The other thing I would have handed out besides the PowerPoint slides and this document would have been the review document, which is this one. Okay. So it looks like that, and it covers Chapter 6 and 7. That one was no explanation needed. You don't need to bother with this one. It's got lines through it. Ignore it. Okay. And then to accompany this, I wouldn't hand it out in, yes, I would. I would hand it out in class. So I'll show you what that one looks like. This is the accompanying document for the review document, which I call worked problems. And this works out problems in detail. Notice when I show you how to balance an equation in the review document, worked problems, I give you steps with these numbers. So the first thing I would have done to balance this one is change the coefficient here to 2. Well, actually, the first thing I did was would do an inventory, and then this step 1, step 2, step 3, and then 1, 2, 1, 2, 3, and then 4, and that balances the equation down here. Okay, so that's the way this document plays out. All right, now let's go back to Chapter 6 PowerPoints and continue our discussion. All right, what we're going to cover today is chemical reactions. Up to this point, we've learned the alphabet, which is chemical symbols, what they represent in terms of elements. And we've learned how to write words, which is chemical formulas, compounds. And now we're going to learn how to construct sentences with those compounds and elements. And in addition, learn what types of chemical reactions that we can classify. First, we need to suspect that we have a chemical reaction, because chemical changes aren't the only changes that occur in nature. Sometimes the changes are purely physical. For instance, the past couple of days, we had physical changes in the moisture in the atmosphere. It was water vapor for a while, and then it turned into solid ice. in the terms of snowflake. But chemical reactions often give these visual clues, and the clues aren't always visual. We're going to look at those first. But that doesn't mean that the reaction is not occurring. These are just clues. So what we may notice is a color change from, say, red to blue or green or yellow. Right? If the color just gets less intense, that doesn't necessarily mean a chemical reaction. It could just mean that we've diluted the solution, so the color isn't as strong. But look for color changes. Look for the formation of solids. When you put two solutions together, sometimes they react to form what's called a precipitate, a solid, which is very, very, very fine particles, but if you wait long enough, it will settle out. And the formation of a solid is one of the indicators of a chemical reaction. Bubbles, right? If a gas forms, then you may have a chemical reaction. Now, we're not just boiling the mixture and changing liquid water into water vapor. That's a physical change. But if you put two solutions together, or put a solid into a solution and you get bubbles forming, then that's a good indicator that we have a chemical reaction. The other is the production of heat or the absorption of heat. Sometimes chemical reactions evolve heat. We call that exothermic. Exo meaning out of, and thermic, of course, referring to heat. Or endothermic, where it absorbs heat, and if you touch it, it'll feel cold. That's called endothermic. All right, here's an example of the evolution of a gas. This is one clue. If we drop a 9-volt battery into water that's got a little bit of acid in it, and wonder why we do that, because acid is an insulator. Water is an insulator. Right? If you try to run a current through water at low voltage, you get nothing. Right? You do not complete the circuit. So you need some type of mobile charge, and we throw some acid in there, hydrochloric acid, or some other acid will work. It doesn't take much. Once you get the current going, then you form gas bubbles at the electrodes. One electrode will form one gas and one will form the other. In this case, water is being split into its elements. Right? So the reaction is, well, I'm not going to show you the reaction because we haven't talked about how to write them yet. So let's not get ahead of ourselves. But that's one clue. Here, a clue is obviously a color change. So hydrochloric acid is added to a solution of cobalt-2 nitrate, and it turns the solution blue. Right? So the indicator there is a color change. That is a chemical reaction. In this one, we're adding sodium dichromate together with lead nitrate. Right? And we form a solid. Notice that those two solutions are clear. You can see through them. But when you add them together, you get a reaction amongst the different ions that form in the solutions, and one of those interactions produces a solid. All right, here's how we write chemical reactions. The reactants always go on the left-hand side, products on the right-hand side, and an arrow in between. The arrow simply means that a reaction is occurring and producing the products. We write the compounds correctly. CH4 is methane. O2 is oxygen. Right? It's one of those diatomic elements, right? Like hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Those are all diatomic. So when we say we're reacting methane with oxygen, you have to know that oxygen is diatomic. If you don't know that and write it correctly, then you will never balance the equation, or you won't balance correctly. And the product is CO2. We know that to be carbon dioxide. And then H2O is water. So that's the way we write them. This is a chemical equation which describes a chemical reaction. All right, there's more to the story. Here it comes. In a chemical reaction, we do not create or destroy atoms. We simply rearrange them. So, all the atoms that are present in the on the reactant side are present on the product side, which means we can count them up and see if we have the same number on both sides. After you write the compounds and put them in their place, then you can count up the atoms of each element and look to see if it's the same on the product side. If it's not, then the equation is unbalanced. That chemical reaction is unbalanced. It says that you have either created or destroyed atoms, and we can't do that. So we have to balance the equation. All right. Sometimes when we have polyatomic ions, remember those? I gave you a handout on polyatomic ions, such as NO3 minus or C2H3O2, nitrate or acetate. In that list will show you polyatomic ions. So when we write the compounds, we know how to name them correctly. Most chemical reactions leave these intact during the reaction, so they can be used as counting groups. That comes later. When we balance equations, I'll show you that one. However, there are some occasions when these polyatomic ions are torn apart. In that case, then you have to count individual atoms of the elements for the reactant side and the product side. This is your author's idea of what a balanced equation looks like. We started out with CH4O2 yields CO2 and H2O. If we count up the atoms, we know that we have one carbon on the reactant side, 4 hydrogens, and 2 oxygens. And we count up on the product side, we have 1 carbon, but we only have 2 hydrogens, and we have 3 oxygens. That equation is obviously unbalanced. If we add another oxygen on the reactant side, and we add another water on the reactant side, on the product side, excuse me, then we can count up the atoms and they balance. Right? What that looks like in terms of a balanced equation is the bottom one here. CH4 plus 2 times O2 yields CO2 plus 2 times H2O. These numbers that we put in front of the reactants and products are called coefficients. And using coefficients is the only way that you can balance an equation. You cannot change the subscripts. The first step in writing a correct equation is to write the compounds and elements correctly. Once that's done, you can't touch them. Those formulas are chiseled in stone. The only way you can change the number of atoms is with coefficients. All right. Sometimes also it's convenient or essential. Oftentimes it's essential to know what phase the reactants and products occupy. We use an S in parentheses for solids, L in parentheses for liquids, G for gases, and AQ for aqueous solutions. Those are the only ones that we're going to deal with. All right. So here's another example. Potassium is on the left, and we're going to combine it with water, and we get a violent reaction, very exothermic. It also produces a gas, and not just any gas, it produces a flammable hydrogen gas. So when that hydrogen gas reaches the surface, it combines with oxygen in the atmosphere, and there's so much heat produced, the flame is ignited. That mixture is ignited, and we produce this flame. And then what's left behind is potassium hydroxide in aqueous solution. Now, what we're describing here is only the reaction of potassium and water to produce hydrogen gas and potassium hydroxide. When you see the flame, that's a separate reaction. That's hydrogen reacting with oxygen to yield water. So we have two reactions going on there in reality. Now, is this balanced? Right, one potassium, two hydrogens, three hydrogens, one oxygen. So the hydrogens are out of balance. This equation needs to be balanced. But we're not going to do that right now. So here we have an example. We have a mixture of hydrogen gas and chlorine gas. So let's write those up here. Hydrogen gas and chlorine gas produces what? Those elements react explosively. It's a very violent reaction, and they produce gaseous hydrochloric acid. Let's do this. Actually, we don't call it hydrochloric acid. I mean, the author of this slide did, but it's not hydrochloric acid until you dissolve it in water. At this point, it's hydrogen chloride. All right. So the author of this slide stands corrected. That's the unbalanced equation. We wrote the elements correctly. We wrote the compound correctly. Right? So it looks like this. This conservation of mass by the conservation of atoms, of the elements, is central to balancing chemical equations and understanding chemical reactions. Now, how did we end up with this equation? We were told what the reactants were and what the product is. Most often, you will have to be told. And if you were to become a bench chemist, some reactions, you would have to investigate them to find out what the products were. Usually, you know what the reactants are because you put them together. But the products may elude you for a time until you have a chance to analyze the reaction mixture and determine what the products are. For our purposes, there are very few reactions from which we can deduce the products. I'll show you some of those as we proceed. But most often, you have to be given the reactants and the products, at least by name. And if we name them, then you've got to be able to write the chemical formulas. That's why you learned to do that in a previous chapter. If you haven't mastered that skill yet, you've got some catching up to do, because we're not slowing down. All right. You can't change the formulas once they're written. That's the golden rule. All right. So these are step-by-step instructions, just for the recording. But I'm going to show you how to balance an equation, and it will follow these steps. Okay, write the appropriate formulas with the correct compounds and elements, and then write the equation, reactants and products, put them in their place, and as practice for now, also write the phases, right? Hydrogen gas, oxygen gas, liquid water. Then balance the equation. Your author and many chemistry textbook authors say balance the equation by inspection, starting with the most complicated molecule. All right. They sort of hedge their bet there. When they say by inspection, they're copping out. They're not actually showing you how to do it. They're giving you hints about how to get started, but they're not giving you any help as to how to balance an equation. Most textbooks, older textbooks, do it that way. I'm going to show you how to balance equations. I call it my budget method. Okay, and we'll let that lie, because I'm going to show you more. I need to clean this slide up. I don't like those visual aids. Then you balance by changing the coefficients. Notice one thing. What are the coefficients for this reaction as it is now? 1, 1, and 1. Just because we don't write the 1 doesn't mean it's not there. If you have a formula written here, it has to be at least 1. And since we don't like redundancy, we leave the 1s off. We only write 2s and higher in there. But this is always 1, 1, and 1 if you don't see a number written. Okay. This is the balanced equation for that particular reaction, but I'm going to show you how to balance an equation in just a second. Now, we could, what this equation tells you, let's stop and make a point here. What this equation tells you is that 2 molecules of hydrogen plus 1 molecule of oxygen yields 2 molecules of water. All right. So what that is saying, and this is often overlooked, what this is saying is chemical reactions don't occur from mass of one reactant and mass of another reactant to produce a mass of products. The reaction is numbers counting. Numbers of hydrogens plus numbers of oxygens plus numbers of water produced. All right, that's key to understanding chemical reactions. It's not mass. Now we're going to learn how to use mass in a chemical reaction, but this balanced equation is purely numbers. This is the preferred method. This is the preferred equation. We prefer the smallest whole number ratios of reactants to products. We could write it 4, 2, and 4, but if we divide the whole thing through by 2, we get 2, 1, and 2. You can remember some math rules. If you have a math equation, something equals something, and you multiply the whole thing through, all operators through by the same number, then you get the same result. So we're piggybacking on math here to explain this one. Okay, these are the helpful hints that are in that document, right? If an element appears in only one place in the reactants or one place in the products, save it to last. And I'll show you why that is in just a minute. Well, here it is. Because when you put a coefficient in front of an element, you only change that element, right? If you try to balance it in the middle of the equation, then you might have to come back and change it again later. Because when you put a coefficient in front of a compound, you're changing more than one element. All right, so we save this one to last in this balanced equation, and that's 6. I keep forgetting to correct that problem. That needs to be a subscript. All right, that's just sort of a corollary of the first one. I'm not going to spend time on that. We tend to save water till last if we can. One of the reasons is that water is often the solution, the solvent, the solvent of a reaction. Aqueous solutions is water, and it's massively concentrated. I mean, it's very high numbers of water molecules, so we don't mess with it until last. Okay, if a fraction occurs, if we need a fraction, now when we present the balanced equation at the end of our work, the coefficients are all whole numbers. But sometimes we can use a fraction as an intermediate step. And I'll show you how to do that in just a few minutes. But we got to get rid of the fraction in order to present the final balanced equation. Here's a little tricky one. If you have an element occurs in one place on either side of the arrow, and the subscripts are odd and even, in this case, we're talking about the hydrogens. Hydrogen's only one place on this side and one place on that side. And notice that the subscript is even here and odd there. Then it's very convenient to use what we call in mathematics as cross multiplication. We take that 2 and turn it into a coefficient on this side, and take that 3 and turn it into a coefficient on this side. And that gives us 6 hydrogens on that side and 6 hydrogens on that side. Now, if the element happens to be distributed among several compounds, you can't do that. It won't work. But if it's only in one place, then this is a neat trick to help you. All right. And the last hint is where we're headed next. I form a table, sort of a table of the equation, and do an inventory of the elements. Now, I'm going to show you how to do that in just a second. And occasionally we'll have polyatomics in there. I mentioned before, polyatomics on both sides. If that's the case, and there's no splitting of the polyatomic in the process, then you can use the polyatomic as a balancing unit. And that saves you a lot of headache rather than having to balance individual atoms. Okay. And this is what it would look like. If we have ammonium phosphate reacts with calcium chloride to produce calcium phosphate solid, there's a precipitate. We have a solution plus a solution makes a solid. And then ammonium chloride is another product. This would be the correctly written compounds. And you should know how to do that by now. Then I assess the balancing groups or elements on the left-hand side. So here's ammonium, right? Ammonium is on both sides, unchanged. Phosphates on both sides, unchanged. calcium and chloride are also there. So then the initial count, right? We have 3 ammoniums on this side, 3 ammoniums. We also have 1 phosphate and 1 calcium and 2 chlorides. Then we go to the other side. How many ammoniums do we have over here? Just 1. You can see right away that using this method, you can tell if your equation is balanced. We have 2 phosphates on this side. We have 3 calciums, and we have 1 chloride. So now, where do we start? Well, we don't have any individual elements off by themselves, so we can't use the first hint. We've already taken advantage of the polyatomic hint. So sometimes, if you don't know where to start, you just start at the top, like with ammonia. Or we could start with calcium. Let me see where I started for this one. Okay, I started with calcium. Okay, so the first step is to change the calcium so we have 3 on the reactant side. So I need a coefficient of 3. Then we do a reassessment, right? Now we have 3 calciums on this side and 3 on the other side. Okay, but we have to reassess the chlorines too. So now we have 6 chlorines. Okay, right? The chlorines are now out of balance. So let's go over to the other side and fix that problem. We need a coefficient of 6 here to give us 6 chlorines. And it also changes the ammonias to 6. Okay, reassess the chlorines. Okay, now we have a 6. So we can see that the chlorines are balanced, the calciums are balanced, the ammonias are not balanced. So let's go over to the ammonias. Third step. And what coefficient would give us 6 ammonias? Well, we've already got 3 inside the parentheses, so a 2 coefficient will give us 6. So now we have 6. And that changes the phosphates to 2. So we reassess the phosphates. And notice that we are now balanced. 6 ammoniums, 2 phosphates, 3 calciums, 6 chlorines. That is a balanced equation. And this is my budget method. I'll do another one on the board here in a minute. I had this one animated just as an introduction. Okay, here we have an equation. And the question is, what's the sum of the coefficients? All right, so there are 2 things here. First, we have to check, is the equation balanced? So I'll write the equation up here. Let's see, FeO. That's iron 2 oxide plus oxygen gas yields Fe2O3. And that's solid. Okay. Notice I left some space here for my coefficients. All right. First thing we do is check to be sure the compounds and elements are written correctly. O2, that's a valid compound with a 2+ charge on the iron. And this one has a 3+ charge on the iron. Right? So we did change the charge on the iron. We'll talk about that later. You just need to know how to write the compounds now. Okay, let's assess. We have iron, oxygen, and that's it. That's all the elements. And there are no polyatomics, so we just go with the elements. Now let's do the budget. All right, we have 1 iron, and we have 3 oxygens. On this side, we have 2 iron and 3 oxygens. So for now, the oxygens are balanced. That may change, but we're still going to hold that one till last if necessary. And we're going to the iron. So we need 2 irons on this side. Right? That makes 2 irons and 4 oxygens. Okay. Hold on a second. Let me see if I did this right. 2 irons. 4, 2, 4, 4. That's right. Okay. So now we got a problem. We got 4 oxygens on this side and 3 on that side. So what I'm going to do is turn an odd into an even. You know how to do that? If you multiply anything by 2, you make it an even number, right? So I'm going to put a 2 over here, right? That changes the iron to 4 and the oxygen to 6. Now I'm going to correct the iron again. We need 4 irons here, right? That changes the oxygens again. So now we got 4 plus 2 is 6, right? Oh, and this is 4. Sorry. Okay, so let's recheck it. 4, 6 oxygens, 4 and 6. We're balanced. We didn't even have to touch that oxygen. Okay? Now, what's the sum of the coefficients? Well, we got a 4 plus a 1 plus a 2. That's 7. So our sum of the coefficients is 7. All right. What's next? Okay, we're going to take this one. Which of the following correctly balances the chemical equation given below? There may be more than one correct balanced equation, but there's one that we prefer. If a balanced equation is incorrect, explain what is incorrect about it. Okay, so there's our choices. Okay, be sure this is positioned. All right, let's write our equation. Calcium oxide, and they're leaving off the phases, plus carbon yields calcium carbide plus carbon dioxide. Okay, so let's tally. We have a calcium, we have an oxygen, and we have carbon. So this is 1, 1, and 1. This is 1 calcium. This is 2 oxygens. And this is 3 carbons. Okay? So we have an element here. We're going to save the carbons till last if we can. That means I would go to oxygen first. Right? We have 2 oxygens here. We have 1 there. So I'm going to put a 2 here. That means 2 oxygens and 2 calciums. Okay? On this side now we have 2 calciums. So let's put a 2 here. And that makes 2 calciums and 4 carbons. And that's all it changes. Oh, excuse me. That's not right. That makes, I had 3 here, didn't I? Yeah, 3. That changes to 5, right? That's 4, but there's an extra one right there. So that's 5. Okay. Now we can balance the carbons. We need 5 carbons here, right? 2, 2, 5. That equation is balanced. Now, the preferred equation is the simplest whole number, which is 2, 5, 2, and 1, right? We can't simplify that any further. So that's the preferred equation. Another one might be, say, 2 times that, 4, 10, 4, and 2. Or we could take half of that and make 1, 2.5, 1, and 1/2. That's what this one says. These are fractions. We don't like fractions. Sometimes we have to use them, but we avoid them if we can use whole numbers. And we use the simplest whole numbers. So the preferred one is Roman numeral 2, and the first one is not accurate. Why? Okay, notice this Roman numeral 1. What's wrong with that equation? Whoever did this broke the rule. They changed the subscript to make it balanced. This is not a balanced equation because they changed that formula, right? That wouldn't balance anyway. Calcium is a 2+ charge. Oxygen is a 2- charge. If you multiply oxygen by 2, now you got 4 minuses, and that doesn't balance. So Roman numeral 1 is wrong because it was balanced the wrong way. Okay, now we can move on. Which of the following statements is false? Subscripts in a reaction must be conserved in the products. No, we don't conserve the subscripts because we write the compounds correctly on both sides. And after that, the subscripts can't be touched. And they don't have to balance. What they have to do is be consistent with the element and the compound composition. So A is false. Coefficients are used to balance the atoms on both sides. Yes, that's true. That one's false. B is true. When one coefficient is doubled, the rest of the coefficients in the balanced equation must also be doubled. In the balanced equation, once the equation is balanced, the ratio of coefficients is fixed, cannot be changed, unless you multiply by the same factor all the way through the equation. Then the ratios are still constant. So that one's true. Phases are often shown for each compound, but are not critical to balancing an equation. That's fair. Yeah, it's not critical to balancing an equation. It's critical to knowing what the products might be sometimes. Yeah, but it's not critical to balancing an equation once you know what the reactants and the products are. So the only really false one here is A. I'm just hammering this point, right? The number of atoms of each element is the same on both sides in a balanced equation. Can't change the subscripts. That is a mortal sin. A balanced equation tells us the ratio of the number of molecules which react and are produced in a chemical reaction. Yes. The coefficients tell us the ratio of the numbers of molecules, or the number of reactants to product ratio. That's what it means. Coefficients can be fractions, although we don't like them. And if we do have to use a fraction, then we want to get rid of it. I haven't shown you that one in detail yet. All right, stoichiometry. What we mean by stoichiometry, and this is I think this is the last slide. I need to use an equation where we have to. I know one. I'm going to use it in just a second. Stoichiometry is the process of using the balanced equation to determine the relative masses of reactants and products. So, using methods of stoichiometry, we can assess the masses of our reactants and find out the mass of products that are produced. but we have to transition from mass into numbers to go from one place to another in the equation, and then transition back to mass. The equation itself is only numbers. So that's why you learned how to determine the masses of compounds, the molar masses of compounds. All right, is this the last one? All right, I'm going to put a sample equation up here. Let's see. I think this one, everybody knows how to operate a propane burner, right? Either your gas grill, or maybe you have propane in your house. Heats the house, cooks your food, dries your clothes. If you're on propane, this is the chemical reaction that occurs if you burn propane. Okay, C3H8 is propane. Add oxygen to it, this is a combustion. It produces carbon dioxide and water. All right. So let's do our assessment. We have carbon, hydrogen, and oxygen. We have 3 carbons. We have 8 hydrogens and 2 oxygens on this side. Now on the other side, we have 1 carbon. We have 2 hydrogens, and we have 3 oxygens. We save the oxygen to last and water next to last, if we can. Come on. Okay, where do we start first? Well, if we're going to save oxygens and water, it looks logical place would be to go to carbon. So we need 3 carbons on this side. Right? That changes the oxygens to 6 plus 1 is 7. Okay. Now we want to balance the hydrogens. We got to go to water. So if hydrogens are 8 on this side, we want 8 hydrogens on that side. That changes 6 plus 4. Let's see. 6 plus 4 is 10. So let's see. We got 8 hydrogens and 10 oxygens, 3 carbons. And now if we put a 5 here, that balances. That wasn't what I was getting at. I was trying to create an example where we could use a fraction. All right, let's try another one. Yeah, let's just erase them all. I know. Let's burn the gasoline in your tank, the tank of your car. It's mostly octane. So octane looks like this: C8H18 plus oxygen yields carbon dioxide and water. Okay, now we're going to assess the same elements. So we have 8 carbons here, we have 18 hydrogens, and we have 2 oxygens. On this side, we have 1 carbon, we have 2 hydrogens, and we have 3 oxygens. Okay, we're going to go to carbon again. 8. That goes for 2 times 8 is 16 plus 1 is 17. Okay. Now we're going to go to hydrogens. So we need 18 hydrogens. Let's put a 9 here. That makes 18 hydrogens. And that's 9 plus 16. Right? 9 plus 16, right? 16 and 9 oxygens, which is 25. So that changes this to 25. And we already did the hydrogens. Yep. Okay. So we got carbon, hydrogen balanced. We're going to oxygens. We need 25 oxygens on this side. But this is an odd number. We can't get 25 out of that. So what we do is we use a fraction. We use 25 halves. Okay? What does that mean? That means we take half of that molecule, which is 1 oxygen, right? And we multiply it by 25. That gives us 25. Okay, now technically, this equation is balanced with the proper ratio. 1, 25 halves, 8, and 9. But we prefer whole numbers. So if we multiply, now that the ratio is established, we multiply all of them through by the same value. And to get rid of that fraction, we just need to multiply by 2. Right? 2 times this is 2. 2 times this half makes it 25. 2 times 8 is 16. And 2 times 9 is 18. Okay? So now the coefficients are 2, 25, 16, and 18. That's what's happening in your gas tank, in your engine. When you draw gas through your fuel injectors, combined with oxygen, goes into the cylinders and reacts with oxygen to make carbon dioxide and water, ideally. Right? We know that there are other gases in there, like incomplete combustion products, like carbon monoxide, nitrogen oxides, because nitrogen is in there with the oxygen. Right? So this is only one of the reactions. This is the way we would prefer. Okay, so that shows you an example of the fraction trick. And we're done for today.